What's up? In this video, I wanted to talk about something that I think is really important and isn't emphasized enough in the space of people that are trying to learn machine learning. And that is placing a heavy emphasis on learning the math and really understanding rigorously the mathematical foundations of the models that you're going to be working with every day. And so I feel like for a lot of people, there are two separate origins from which they approach machine learning, AI engineering, whatever you want to call it, data science in general. You've got people that are coming from a computer science implementation focused background, and you have people that are coming from a theory based mathematical background. And the people that are the best at these jobs are the people that have strong foundations in both and are able to blend these things together and take the theory when it's necessary and implement things well. You're not going to get by only doing one. If you know the theory inside and out and you can explain exactly why a model works, but you can't implement it, and you've spent too much time thinking about it to the point that you don't know how things happen when you're working with that model in a real environment, that's not tremendously helpful. Having a good foundation is incredibly important, but also being able to apply it is really, that's the end goal, right? But conversely, if you're one of these people that is coming from a background that was very implementation and hands-on focused, but sort of neglected the theory, you're also going to be at a disadvantage because when your model doesn't do well or things are performing suboptimally, that's when you go back and you consult the theory and you say, okay, why might this not be working? What can I change? What are things that other people have tried in similar situations which have helped them improve their results or at least identify what's going wrong? So that's just what I want to say off the bat, is that this isn't an either or thing. Both sides, both schools of thought, both origins of this field are incredibly important. The hands-on computer science aspect as well as the foundational mathematical aspect. But I think it goes without saying that the latter is neglected to a much greater extent. A lot of people don't have an appreciation for the math, either because it's difficult or it's tedious to work through, or they just really don't want to spend the time to learn and understand it. But I think this is a tremendous mistake, and I'll talk about a few reasons why I think this is the case. But to start, let's just talk about what makes you an effective data scientist or machine learning engineer or whatever. It's not going to be, oh, this guy has implemented this algorithm before, he knows how to write the code to make the algorithm work. Most algorithms that you would learn about in school have already been implemented in a billion different languages by people that have optimized it way better than you ever could. Like, for example, if we're talking about neural networks, I've written my own neural network before. Was it optimized? Certainly not. Was it super robust in all the features that it offered? No, not really. It was super instructive, and it helped me understand what I was working on way better. And it was something that I would recommend that anybody do if you're into deep learning. However, I would never choose my personal neural network over one that's implemented in PyTorch, because I know the people at PyTorch have spent a ridiculous amount of time trying to optimize the shit out of their framework and make sure that the people that are using it are getting the best experience with the minimal overhead. And so what I was getting at with that, though, is knowing how to implement stuff is helpful, but really the implementation's already there out of the box for you, and they're done much better than you probably can do individually. And so the majority of your job, whether you're in academia researching or you're in the industry, is going to be taking these existing components and arranging them in a way that produces a good result. So what I mean by that is saying, you want to build an image classification pipeline for a research project. You can go and build a convolutional neural network from scratch and implement the backpropagation and spend 3 months learning tensor calculus, or you can understand the high level of how a convolutional neural network works and then leverage an existing framework like PyTorch to get it done way faster. And so that's what the majority of your work is going to constitute. It's going to constitute, okay, we've got this framework, we've got this library, we've got whatever that enables us to take these machine learning models, which I've learned in the theory in the classroom, and apply them, and now we want to evaluate them on a real world task. It's no longer sufficient to just know how to implement stuff out of the box. Really, what's going to differentiate people is how deeply do they know the theory that they're working with. Because at this point with AI, pretty much anybody can do an implementation. Unless you're doing something really weird, AI has seen millions of explanations of implementing linear regression or neural networks or decision trees, anything that you can think of. Even more advanced and arcane stuff, AI has seen plenty of times and can pretty consistently implement using these existing frameworks like TensorFlow, scikit-learn, etc. And so, what is the gap between you and another machine learning engineer, given that if initially it was just you were really comfortable implementing all these algorithms, you knew how to make the code work to accomplish what it was that you did. Even before AI, these frameworks made it pretty easy, so you didn't have to be a domain expert. But still, there were still times where you had to trudge through the implementation details, and you had to read the docs, you had to be familiar with the framework, etc., etc. With AI, that's much less of the case now. And so if your edge previously was that you were well versed in the programming aspect of it, of either implementing things yourself from scratch or from working with these existing libraries and being really knowledgeable in the framework, that edge has disappeared. And so what is the remaining edge that you have as a candidate in this sort of job market, if these are the sort of jobs you're pursuing in data science and machine learning? Well, really, you have to think about what is the AI not good at doing right now. The AI is not good at making human decisions. It's not good at looking at granular information and making calls that are partially informed by data and partially informed by vibes and intuition. It's really quite bad at doing that right now. And if you don't believe me, you should start using Claude Code, because I've been using Claude Code on certain projects, and sometimes I give it too much freedom in building things out, and I have to go back and be like, no, that's not the right way to do that. That's not maintainable. That's a bad pattern. We need to fix this. And generally, if you don't be upfront with the AI model about that sort of thing, it's going to regress to a pretty subpar mean as far as the output that it's giving you. But regardless, I digress. The point I'm making is that these AI models are not very good at making these human type decisions. So that's where you have your edge between other people, because everybody has access to AI more or less. And so the whole implementation and technical coding side of it is less relevant if you are a machine learning engineer. What's more relevant is your brain and how you understand these models and your understanding of the theory. And when I say theory, really what I mean is the math, right? So you could understand generally how a transformer works, but until you've seen the implementation yourself and you understand how attention works, you understand why you're applying layer norm, what layer norm is doing statistically to the features of the function and why that's necessary, until you understand deeply automatic differentiation and how some of the things we're doing, like residual connections and layer norm, tie into the mechanics of making sure that automatic differentiation is able to be performed smoothly, then really you are not going to be able to optimize and tune your models very well. Moreover, if your model was not training well, maybe you could just keep sweeping through hyperparameters and hoping that eventually you find a combination which permits your model to train well. However, if you have a background in the mathematical foundations of stochastic function optimization, let's say you're using stochastic gradient descent, for example, and you keep getting stuck in local minima. If you understand the theory of, hey, I'm optimizing a stochastic function, what can I do to help try to avoid local minima? Well, you could say, I know that I can use momentum to help try to perturb, the descent of the loss function out of local minima, and then hopefully reach a better local minimum, or maybe if you're lucky, a global minimum. Additionally, if you understand the math of how the math of how the calculations in a recurrent neural network or a transformer or a convolutional neural network works, then it demystifies a lot of why it's doing what it's doing. If you understand how, let's say, average pooling or mean pooling or max pooling works, you're able to appreciate, okay, I understand what's going on under the hood. If my model is not doing well, maybe I could look and see, okay, is it average pooling, is it mean pooling, is it max pooling? How might that be influencing the hidden state and the eventual output of the model? And so really what I'm talking about is a strong foundation of the theory, but you really can't understand the theory unless you understand the math. At the end of the day, a lot of machine learning is just optimizing functions. And so if you don't understand the math of how that's being accomplished, then you're really just kind of you're going to be taking shots in the dark as far as how you tune your models, how you implement maybe custom models, or how you take existing models and try to fit them onto your specific task. So in order to understand these new architectures and all of these new papers and stuff, you really need to have a strong mathematical foundation, because if you're reading a new paper about a new function optimizer and you don't know the difference between a deterministic and stochastic function, or you don't know some of these key concepts of things like momentum, then you're really not going to be able to appreciate whether, hey, is this new function optimizer something that I could apply to one of my problems? If you don't understand these theoretical components and the math that describes why they're relevant and why people use them, then your guess is really no better than just asking Claude, saying like, hey, is this going to work, dude? And maybe Claude says yes, maybe it says no, maybe it's right, maybe it's wrong. If you don't know the math, you can't verify that independently yourself. Really, I'm of the opinion that if you can understand the math of a system deeply, everything else becomes trivial. If you understand the math of machine learning, then everything else downstream is trivial. And it's easier to learn, in fact, because you know the math that underpins it. I would imagine the same goes for physics, where physics has some extremely complicated math in it. But if you're strong on the math helps illustrate and illuminate why it's being used. You can understand, oh, I understand why a tensor is being used in this situation. I understand why various calculus concepts are being used, and in doing so, it makes the system you're studying easier to understand. The exact same thing is true in machine learning. If you don't understand why certain mathematical concepts show up and why they work in certain problems and certain models, then you're really not going to be able to apply those models intelligently and know how to search for a model that is going to fit onto a novel problem which you've encountered. And so really a lot of rambling has gone on today just for me to say that I implore you, if you're trying to get into data science and machine learning and you're just doing, you're implementing linear regression, or you're doing you're just fitting models to data sets rotely, and you're not thinking about the math of why you're selecting the hyperparameters you're doing, why one model works better than another, why certain conventions are made in designing the architecture of a model, then you're really not setting yourself up for success. And the only way to understand those things deeply is to analyze the math that underpins the decisions as to why people decided to build models and apply them in the way that they do. And so I implore you, if you don't get anything else out of this video, it's that you need to learn the math. You can't shy away from the math. And if you commit to it and you really understand the math, that my monitor just turned off, so sorry about that. But really, if you truly understand the math of the system you're working with, whether it's in machine learning or anything, then you will have a much better understanding than most other people, and it's going to empower you to learn things faster, do things faster, and make better decisions that lead to better outcomes pursuant to whatever you're trying to accomplish, whether it's training a model, understanding a system, or designing some sort of engineering solution. So yeah, that really reaches the end of what I wanted to convey in this video. Let me know your thoughts. Do you agree with me that math is extremely important for machine learning? Do you think it's secondary? Do you think something else is more important? If you disagree or if you agree, let me know, and I would love to discuss that with you guys. Have a good one.